So, hello everyone. I think we can start. Today we will have the second practical session where we will learn how to do the simulation of the aortic valve by using our open source multi-resolution and multi-physics solver, SPHinXsys. Today, Wudong will talk about the detail. So, Wudong, you can start.
Yeah. Let me first share my screen. Okay. Hello everyone. Welcome to the second numerical modeling practice. Today we will have a FSI case named aortic valve case. So first like last time we should download the code from GitHub and download the release version code. And another thing is go to the go to the model. Download the case, the source code of the aortic valve case. Also, we save it in the same place. And we have these two here. At the desktop here. And unzip name. Also, and then copy this one into the SPHinXsys source code and put the name here. So next, we should use CMake to build the SPHinXsys. Before this, we should create a new file folder named as you like. I named the SPHinXsys build. And open the CMake. Here we choose desktop, we choose this one, the source code. And browse build, we choose net, we just build and just create. Okay, choose this one and configure. Remember here, should choose X64 and finish. And then generate. Click generate and then open the project. So in this way, we can see it the solution explorer. We can see here. We have the this case, this source code here. So we open the main function. Okay. And right click this, choose set as startup project. Okay. So in this way, we will run this case. So we go to this .cpp file. First, we see this line. Actually, as we said last time, this line gave us all the declarations. Then we also import the SPH namespace, which includes nearly all the symbols used by SPHinXsys. So next, we give the basic geometry parameters. These are the parameters, and we go to the PowerPoint. Let me show you the case. And in this case, we named the aortic valve. So actually, this case is a 3D case, but we simplified this case to 3D case. So we named the two-dimensional representative of the aortic valve. So the 2D case is look like this. Look like this picture. And we have the leaflet. This one leaflet is a linear elastic body, and we have a sinus cavity here, and I also give the values of the parameters here. I want to explain this one, DL sponge. We define a sponge area at the beginning of the inlet. Sponge area makes the inflow more stable. So let me go back to the code after we have the idea about the case. This one. So we give here channel length, height, the cavity radius, the leaflet length, leaflet thickness, and here we give the particle number for creating sinus cavity. So this one I will explain later. Okay, let me go to next. We define the sinus cavity center, and this one actually global reference resolution is the spacing reference spacing, particle spacing, particle spacing, and the DL sponge BW. BW is the boundary width. I showed here is boundary width. It's normally the 4 times of the particle spacing. The channel boundary. Okay. Okay, it's a need to slowly for change the frames. Okay, I forgot one thing. Let me close this. And this one means the length of the constrained leaflet. So we go to the boundary box. Boundary box gave here we give the coordinates of the lower and the upper bounds of the domain. Yeah, upper bounds of the domain, which will be used as the bounds for mesh used for building cell nucleus. And then we give the material properties. For the fluid and also for the solid. As we are using a weakly compressible model for imposing incompressibility. So the maximum speed here in the flow, we give the max speed in the flow and the artificial sound speed of sound. Then we go to the how to generate this model. Because here we first define how to create a fluid block shape. This one actually we give a series of points, 0.1, 0.2, and these points. Let me show you the details. So we gave the 0.1, 0.1. I gave it here 0.1. And I gave 0.2, pushback 0.2 as the code set, and pushback 0.3. And at this semicircle, I gave endpoints. Endpoints are placed on the semicircle using a for loop, and then gave this point and this point. But remember, gave the 0.1 again to generate a closed geometry. And this way, we generate this shape, but we should then subtract the leaflet. So I don't show here. We can see in the detail from the code. So this one generate the a fluid block shape, and we should jump to later because here just define the shape but not generate. So we jump to create a word block. Actually, we create here. We define create here. So first we create word block shape and create a leaflet shape, and then use add command to add the word block shape, and use subtract command to subtract the leaflet shape. In this way, we get the word block. Okay. Let me go back to the next. We generate the buffer shape, the sponge shape. Here it's same. Actually, we give the four points, and the last point is the same with the first point. So remember this point. It's same, and then it's simple, and then create the outward shape. Outward shape is a little complex. Let me show here. So first, we add a rectangle first, and then add a semicircle. The semicircle generator is same by the by a for loop. And we first generate rectangle and add a semicircle and subtract a rectangle, the small rectangle, and then subtract the fluid body. Add a leaflet. So in this way, the inside the body should look like this. Okay, let me show you first. Should look like this. And we also should define the constrained body. In the code, I named the constrained body as leaflet base, defined by the inside body subtracts the leaflet. So let me go back to the code. This one is the first rectangle. This one is the semicircle, and this one named the inner wall is the second rectangle that should be subtracted. Okay, and define the leaflet shape. First, we give the 4 points of the leaflet. So here we create a leaflet shape. Okay. And before we learned how to create a water block, and then let us have a look at how to create the inside body. Actually, it's same way we define the outer wall shape 1 is the first rectangle, the shape 2 is the semicircle, and the inner wall shape is the second rectangle, and the water block shape, and this one is the leaflet shape. So as I showed in PowerPoint, I should add the first rectangle, add the semicircle, subtract the second rectangle, and then subtract the fluid block, and then add the leaflet shape. For the inside the body, one point we should remember, it's better to make the solid part smoother. At this case, we call this function as relaxation. So we should use the class level set complex shape to define the inside body. Okay, and here this line is also different from the water block. So this particle adaptation, we have 2 parameters. One is this one is the smoothness ratio, and this one means let me show here. the 0 means the n is equal to 0. In this way, the particle spacing is equal to the initial particle spacing. That's to say, the particle spacing in the code is the same with that we gave in the main function. So if we change the 0 to 1, and it means the particle spacing is equal to the half of what we gave in the main function. Okay. Let me. So here, then we give the inside body material properties. Yeah, the leaflet base, as I showed in PowerPoint, we should subtract the leaflet at the end, and above is same with creating the inside body. Okay, and we create an inflow buffer in the sponge area here. And we define the parabolic inflow. Parabolic inflow is actually look like I also write the equations here. We give the U reference and the T reference. Use U reference, we use this sign function to calculate the inflow average velocity. The average velocity look like the time curvature is look like this, and then use the U average in this function. Yeah, in this function. So the maximum velocity is the 1.5 times of the U average. So this function actually is a parabolic distribution at the inflow. So this is the parabolic inflow. How to define the parabolic inflow? It's same as I showed in PowerPoint. So let me go to next. Then we define the leaflet observer body, and the observer point is located at the middle of the end of the leaflet, and we define the fluid observer. It's same with the first practice. We define 21 observer points when the position x is equal to 0. That's the end of the sponge area when the x is equal to 0. And the points are placed from here, start of the measure, from the 2 particle spacing above the channel bottom. Okay. So after the define the model, define the material properties, define observers, we go to the main function. First, SPH system is created, and here, here these two lines is used for whether we use the particle relaxation. So actually I showed you at the first time. Actually, at the if you want to run this code the first time, if you want to use the relaxation function, you should run this code like this way. Okay. Oh no. Like this way. Should first time should change this false to true, and the relaxation function will be used, and but you should run the second time, changing this one to false, changing this one to true. So in this way, you use the relaxation particles at the second time, and you will get the smoother solid body. Okay. And then we define the restarted step is equal to 0 means whether the computation begin from restart file is checked. If here is 0, no, we will don't read the restart file. Okay, and then actually here we create a body. Before we just define a body, and create order block and the order block material, generate the fluid particles, and then we create the inside body. It's the same. Okay, and then we create the observers. Remember here, observers is defined by the base particles. And the way comes to define simple data file input and output functions. Define the write real body status. Why here named the real body? Because the observer particles, the observer body is the fixed body. We don't generate the particles for observer points, for observers. So it's a fixed particles for observer body. So we name here, we write a real body status. And we also define write a restart file, read a restart file. Then we go to the topological relations. We typological relations specifies the possible interaction bodies for each body. For example, for this line, we use the class complex body relation to define the water complex. It means the water block inner will be infected by the inserted body. So then we comes to the here we check whether run particle relations for body fitted particle distribution. Well, we will go back details. Okay, because the last time I forgot this part. So after the explain of the code and before we run this code, I will explain the relaxation function. Okay, let me just jump to the define your numerical method. And in fact, the comments and the variable name makes it pretty clear what we define. Yeah, we have the comments, we have the long name. Actually, using these two, we know this line what we do. Yeah, it's clear. So this line we create we created the configuration for an elastic insert body, and then we comes to the method used for time stepping. So first initialize a fluid step and define how to update the density by summation, how to get the fluid at the vacuum time step size, and get the fluid time step size. Okay. And these two lines actually is the fluid dynamics we calculate here. And then comes to calculate the viscous acceleration and how to calculate the transport velocity correction. And the viscous acceleration and transport correction. And then we define how to compute vorticity. Okay, and we define the inflow boundary condition and the periodic condition. Why we use the periodic condition for the flow boundary? Because we need to keep the total number of particles same in the whole domain when calculating. So we put the particles that flow out from the channel at the channel entrance. That means That means we do this is the flow out particle position x minus the length of the whole domain. So in this way, the particles that flow out from the channel, we put these particles at the entrance. So in this way, we keep the total number of particles same. So it's the reason why we should use the periodic condition. And next we define the algorithms for FSI. So we first define how to calculate the fluid mesh force and inside body, and also the viscous force. And calculate the average velocity and the acceleration, and calculate the then we comes to the algorithm for solid dynamics. First we calculate the time step for the solid part, and then we comes to the solid dynamics, these two lines. Solid dynamics. Calculate the dynamic equations, and then we define how to constrain the base, the leaflet base. For the SI case, we should calculate the normal direction of the solid part. Here we come to define how to write total viscous force on inside body, and also how to write the observer parameters. Okay, then we come to the pre-simulation. Including check whether user relax the particle distribution, and initialize the cell linked list, initialize inner, okay. So we should run a periodic condition in the first time before the configuration build up. Okay, and then we initialize the system configuration for all bodies, and also calculate the initial normalized direction, and also need the computer the calculate the linear reproducing configuration for the solid body. Okay, and then we comes to the time stepping. So the first we check whether we read the restart file. Okay, and if we use, we should read something from the restart folder. For example, the cell linked list, the configurations, something like that. Okay, then we comes to the first output. write the initial real body states, write the initial leaflet tip displacement. And then we comes to the bicycle control parameters for the simulation. We define the restart step, define the screen output interval. It means output frequency, and the restart output frequency here. And we define the total simulation time, the interval for writing out the files. Okay, and we define some time step size. dt is the advection time step size for fluid. This one is the acoustic time step size for fluid, and dts is the acoustic time step size for solid. It's clear here. It's clear because the comments. Okay, and we also define the integration steps here. One is for fluid, one is for solid. And then we comes to the statistics for computing time. This two line is to calculate how much time we used for running this case. And then we comes to the main loop. The computation is carried out with a dual criteria time step scheme. So you can find this serial in a PDF documentation of SPHinXsys. You can download it from Moodle. And we go into this for details. So first we check whether the physical time is smaller than the running time, the end time. And then we initialize the integration time. If the integration time is smaller than d time, the d time is here. The output frequency is smaller than this one. We calculate the the advection time step size dt, and calculate the fluid density, the viscous acceleration, and the transport correction, and the FSI viscous force, and the normal direction of the inside body. And if the we also initialize the inner integration dt and the relaxation time. So if the relaxation time is the summation of the dt. So dt and the dt is the fluid time step size. Okay, the free time step size is okay, it's defined before, and way if the summation of dt is smaller than this dt, we calculate the fluid dynamics. Okay, and in this loop, we also have another loop here. If the DTS sum is smaller than DT, DTS sum is the summation of the DTS is the acoustic time step size for the solid part. So it's several time step size, and we also output the time step here. Here we first output the value of the dt, and how many fluid. This one is the fluid acoustic time step size. So here's how many acoustic time step size, how many fluid acoustic time steps are there in dt. Okay, and we also output this one. This one means dt divide dts. It means how many solid acoustic time steps are there in a fluid acoustic time steps. So it's a little complex for understanding the different the three time steps. First, we have the this dt means the output frequency, and this dt is the fluid time step size, and we also have the dts is the fluid. No, dts is the solid time step size. So and after the this while loop, we go to update something. For example, the cell nucleus, the configuration, and then write the if deep displacement. After this, you can secure this while loop. Yeah, this while loop, this while loop. So we end here. We end here. After this while loop, we write the output files. Okay, and we have another while loop, this while loop. So after this while loop, the calculation ends. So after this while loop, we will get the screen will output the total word time for computation. Note that the total computation time has excluded the time for writing files, because we actually is exclude the time for writing files. So now we can run this case. Before this way, as I said, we should go back to have a look at the relaxation function. Relaxation function here. If we want to run this function, we should change here to, oh no, 2. And if here is 2, then we go into this if sentence, and actually we can run. Let me run this relaxation first, because it needs some time, and then I will explain this lines. So let me run this case first. What the computer what is running it's the first running, so we get the relaxation particles. Okay, and let me explain the slides. So first time we define how to random the solid body particles. Okay, this 2 line is define how to write the files, the reload file, the real body files, and then calculate the relaxation time step. Okay, and then we go to the particle relaxation. And here we random the particles once. And we calculate the surface bounding of the a solid part. Okay. Okay, we go to this part. It should run. Okay, anyway. And then we go to a while loop. In the while loop, we many run this line, run the relaxing step in there. This is the output the relaxing steps for the inside body, as shown here. We should wait a minute, wait a second. It's the output screen. So show here we show the speed of sound, show the something else. Why it's so slow to get the relaxation particles. Okay. And after the relaxation, and the screen will show this line, the physical relaxation process of inside body finished. So here we write the reload file to the reload folder because we have the reload folder. Let me show you here. Go to the build folder, user folder, and here we have the reload folder. And after the relaxation process, we will have the smooth particles in the reload folder. Okay. Now, let us have a look at the screen output. I know why it's wrong, because we should change here to release. Because when we use CMake to build the project, this project we use the CMake build type release. So when we run this code, we should change here to release. Okay, and let me run again. And for the main loop, it's a little complex. I think you should have spend some time to learn it. At one while loop, now are several while loops. So you should take time to learn this part. Do you have any questions? Because before we get the results, we need some time. Let me do some preparations for read the files. We use the parallel view, an open source.
Tom, are you still here? I think Mr. Wu lost his connection, and maybe we can wait a few minutes.
Okay. Now it's a problem for my computer, maybe because I'm offline for a while. So let me continue this. Okay, we go to the we want to have a look at the relaxation process. So we go to the desktop and read the relaxation process output file. So go to the output, go to the cast user here, src output, and let me read the okay, this one. Output. Yeah, read this one and apply. And apply. And show you the change here to point Gaussian. And then fit. And the way smaller. Oh no. And now it's still a problem. Let me try again. Why? What happened? Wait a minute, because I use two computers to one is for the voice, one is for the share screen. So now it's another computer offline. So I will try again. Okay. Okay, because we use two computer to one is for voice, one for the share screen, and the one for sharing screen is offline. So I will try. I will try. Let me try. I hope this time is okay. Let me show the particle relaxation process. This is the first step of the process is the relaxation process. We first random the particles like this, and then we go to the smooth process. And you can see here it's smoother. Okay. And then we run a second time. We changing this line to false. Okay, it's already false. And we run a second time. Because the FSI cases should spend some time to run the code, so I run this code before the class, and I can show the results directly. So this one, which I show the incited body, it's the smoother body. Okay. And this one is the fluid body. We delete this first, and I will show you how to use this function later. And I can show you the velocity field. It looks like this. And I want to compare the particles without relaxation. The results look like this. This one is the results without relaxation. You can see these two results actually different because the smoother particles we get better results. And I can show you the velocity vector field, and I use the graph, and here I choose the velocity, and also here velocity, and apply. So it's here we get the velocity vector. And we can make it larger. You can see the vortex direction. These two is the same, but this This one is the opposite direction. And we can change some parameters to see what happened. Let me check the let me check this one. The thickness of the leaflet. Let me change it to 0.4. Okay, and let me look at the results and show them here. Let me make this particle size small. Okay. This case, the leaflet is thicker, and I also show the show the velocity. And the solid body show the 1 mid-size stress. So the results look like this. Okay, and as I said, I also want to show you if where are you? If I change here the particle adaptation 0 to 1, let us also have a look at the results. I also have a results before, so I show you directly. You can see here for the solid part, we get more particles. Okay, and I also show the velocity. And for the solid body, I want to show the stress. Okay. So it's the end of this class. So do you have any questions?
So if there's no other question, I think we can close here today.
Yeah.
Thanks.